Welcome to Engineering Simplified. Ever wonder how a hospital, a data center, and a skyscraper all stay cool on the hottest day of the year without a single AC unit in sight? The answer is the chiller. Let's break it down. A chiller is a machine that removes heat from water or another fluid and pumps that heat somewhere else. That chilled water then circulates through a building to cool the air or through a piece of industrial equipment to keep a process running at the right temperature. A chiller isn't the same as an air conditioner, even though it does a similar job. A standard AC unit cools air directly. A chiller cools water first, and that cold water becomes the cooling medium for everything downstream, whether that's an air handling unit, a fan coil, or a production line. Underneath all of that, a chiller is really just a heat pump moving energy from one place to another. It doesn't destroy heat, it just pulls heat out of the water and dumps it outside. That movement happens through 4 core components working in a continuous loop. The compressor pressurizes a refrigerant gas. The condenser rejects heat from that pressurized refrigerant to the outside. The expansion valve drops the pressure back down, and the evaporator uses that low-pressure refrigerant to absorb heat straight out of the building's water loop. A chiller never works alone. It's paired with pumps that push chilled water to wherever cooling is needed, and often a separate condenser water loop and cooling tower to finish rejecting that heat. If you're enjoying this, like, comment, and subscribe, and check out the other Engineering Simplified playlists. Chillers generally reject their heat in one of 2 ways. Air-cooled chillers sit outside, often on a rooftop, using fans to blow air across the condenser coils. Water-cooled chillers sit indoors and send their heat to a separate cooling tower. Air-cooled units are simpler to install, take up less space, and cost less up front. Water-cooled units cost more and need that extra cooling tower, but they run more efficiently on large loads and tend to last longer. You'll find chillers doing very different jobs depending on where you look. Comfort cooling in office towers and hospitals, process cooling in plastics manufacturing and food production, where equipment needs a stable temperature to work correctly, and increasingly, cooling the servers inside data centers, where heat removal is just as critical as the electricity supply. Capacity gets described differently depending on who you ask too. Engineers in the US usually size chillers in tons of refrigeration, a unit that traces back to melting a ton of ice in a day. Most other countries just use kilowatts. Almost every chiller you'll encounter uses vapor compression, an electrically driven compressor doing the work of pressurizing the refrigerant. Some facilities use absorption chillers instead, which use heat from steam, hot water, or a gas burner to drive the cycle. Absorption chillers matter most where there's already abundant waste heat, like a combined heat and power plant, or a factory already generating steam. That facility can put heat it's already producing to work cooling the building instead. The common mistake is assuming air-cooled and water-cooled chillers are interchangeable and picking whichever is cheaper without checking the actual cooling load. Air-cooled systems lose efficiency as outdoor temperatures climb, and many building codes cap how much air-cooled capacity is even allowed. Get that sizing wrong, or skip planning for a water-cooled system's cooling tower and the structural support it needs on a roof, and you end up with a chiller plant that either can't keep up with the building's heat load or that never should have passed a structural review in the first place. So remember, a chiller removes heat from water rather than air. It relies on the same 4-part refrigeration cycle, whether it's air-cooled or water-cooled. And the right chiller for a job depends entirely on the building's size, its cooling load, and what heat sources are already available on site. That combination of heat rejection method, cycle type, and correct sizing is what keeps a chiller plant running efficiently every single day it carries a building's cooling load. Drop a like, comment the topic you'd like to see explained next, and subscribe. It genuinely helps this channel grow. See you in the next Engineering Simplified video.